We're going to look first here at example one from the mechanical system set of notes. And in this problem, we have a cantilever beam when it's clamped to ground. There's a particle of mass m that's attached to the top, and then there's a force F of t, a prescribed force, which is acting there at the top. And what we want to do is end up with a differential equation of motion for that system, where we're along the way going to be modeling this beam particle system as simply a spring mass dash pot system with a force F which is applied. Let's first though look at the physical system here of the beam. So the beam has an unstretched position that looks like this. Okay, and let's say that we just apply a static force F to this beam like this. I'll call it something other than lowercase f. I'm just going to be calling some static force F which it is applied, and we know that the deflection here at the top will measure that as a delta. And what you've seen before in strength of materials is that if you make a plot here of the deformation at the top of delta in terms of this static force there of F, you end up with a straight line relationship where the slope of this is given by K. That's an idealized version of the beam. That's what you studied in ME 323. But in actuality, the beam really doesn't behave in that way, depending upon what kind of material that is making up the beam. The actual curve will probably look more of something that looks like this. It's going to be a non-straight line like this. It will probably tend to soften. That is, the slope of it decreases as the deformation increases. But the idea here on linearization is that we find the slope of the curve at the origin, where delta is 0, and the slope of the green line is going to be represented by the stiffness of that spring called K. So that's the background for this. I guess in addition to the stiffness of the beam, we're also going to account for some energy dissipation. As that beam bends, it's going to dissipate energy. In a way, we're going to represent that by dash pot of a damping coefficient there of C. And I guess a very important point that's made here is we're going to model the beam simply as a spring. In other words, all the mass is going to be at the particle there at the top, no mass there in the beam. So that's the justification we go through in order to replace the beam by this spring mass dash pot system. Okay, so step one, our FBD. Draw the free body diagram of the spring mass dash pot system that's shown. The easy forces here are the applied force F, like this. And then we have a spring force there at the top, dash pot force there at the bottom. We note that the sign convention for X is positive to the right. That's a very important thing to observe before we draw the arrows in on our forces for the spring and the dash pot. If I write this as K times X, that represents a magnitude of that force. The left end of the spring is fixed, so the only way the spring is going to develop a force is if the right end moves. And if the right end is at a position where X is plus, in other words displaced to the right, then that spring is stretched. Okay? A positive X stretches the spring, and the spring which is stretched is going to pull, in other words to the left. The dash pot force, very much like the spring, depends on the relative motion of the two ends of the dash pot, except here the force depends on the relative velocity rather than the actual relative displacements. So this is Cx dot. If x is increasing, if x dot is plus, then the dash pot is pulling back on that block. In other words, the force is acting to the left. That's pretty much the hard part of the problem, because Newton is going to give for us the summation of forces in X, and this is again another place where we need to reflect back on the sign convention. Sign convention X positive to the right dictates the sign convention on the forces, so therefore the spring force acting to the left is a minus kx, minus cx dot for the dash pot, applied force F, and Newton then says that that's m times the acceleration, which is x double dot. So we're pretty much done. We got mx double dot. Bring the dash pot force over in the same side. That's a cx dot. Spring force on the left side, and that is equal to the applied force F of t. So that is our equation of motion. So it really came down to getting the right direction on the spring force and the dash pot force based on the sign convention, and our sign convention again was defined at the beginning as being positive to the right. I guess in alternative way, if the problem had been done this way, we could have said that x was positive to the left. There's really no real reason why I said x positive to the left, but in that case, then our spring force, I'll draw it in blue to contrast it with what's above there, is still magnitude of kx, but with x being plus, that means the spring is compressed, and a positive x dot, in other words moving to the left, is going to be resisted by the dash pot, so that dash pot force is also to the right. I think you would agree that this and this are really one in the same when you consider the differences between the x positive to the right and x positive to the left. One final point I would like to make is that we need to make sure that the signs of these terms on the left hand side are all the same. In this case, they're both plus. Why is that? Well, you'd have to think back to maybe some things you saw in differential equations, or maybe we talked about a little bit in 274, is if you have a negative sign on C and or K, it's a problem, because that would correspond not to oscillations, like you would expect from this, but due to sort of an exponential growth. So negative signs are, in this case, not correct because it gives you response which doesn't make sense. Okay, we'll later on in the course we'll actually see some physical systems where C and or K may be a negative, but for oscillatory systems like this, they should always be plus. Use that as a guide at the end, not to get your equations of motion, but more to check them. If the signs are wrong, go back and find out where you went wrong. If you have any questions on this, please don't hesitate to let us know. Get on the blog or send me an email.